Today's speaker is Karim Adiprasito, and he will talk about Lefschetz beyond positivity. And it's okay. It's not the title he gave, but it's the title on the slides. Yeah. Okay, I would say, go ahead. It's your stage.
Can you hear me? Okay, good. All right. So looking at the other talks, I feel a little out of place at the conference. What I'm going to talk about is some recent developments in combinatorics, where we have been able to show things that have been classically associated with scalar structures beyond scalar structure. So in particular, things like the Hodge Riemann relations, the Lefschetz theorem, and things beyond Hodge Riemann relations even. So in positive characteristic that we will talk about. All right. As I said, it's somehow I felt somehow I don't know how much of this area you know. So I'm going to give this more as a colloquium talk rather than a research talk, because it felt a little more distant than to the other talks and comfortable for me. So it will be rather basic for the most time. So I start with a guiding problem. Okay, so I start with a problem that is very simple to understand, and this is kind of the guiding problem in much of this research. So here's the basic problem that you can consider. So you have a graph into the that you want to draw into the plane. Maybe somehow you're trying to play Deutsche Bahn, although somehow they don't seem to be so good at it. And so you have some locations, right, some cities, and then you want to connect them by roads or rail lines. I could use a different color for the rail lines, maybe. All right, so like this. And because you're Deutsche Bahn, it's not good if they cross. I mean, you have enough problems as it is. So let's do it like this. And then at some point, you see that if we add maybe another city, then, well, I mean, you cannot draw all the desired chain lines anymore. So there will be one that you have to kind of forgo, and this city will not be directly connected, right? And so the basic question is, well, if I am not allowed somehow cheating by having double cities connected to itself or two cities connected twice, well, how many of these rail lines can I draw? And it's a basic result that the number of roads that I can draw here is at most 3 times the number of cities. And this really goes back to Euler. The idea is, all right, so if I go back, that's very good, I can go back. All right, I can always draw cities until I have a triangulation of my ambient space. And once I have a triangulation of my ambient space, I can just use Euler formula. All right, and sorry, every bounded or every region now is a triangle, and then I can use vertices minus edges plus. Let me actually. Can I go back? No. Let me just pretend this is a triangle. Is equal to 2, and then I have some double counting, right? So I have that 3 times the number of triangles is 2 times the number of edges by just counting the triangle edge incidences, and then I get this inequality. So it's a really basic result, right? And so here's the guiding problem, or one of the guiding problems that are solved by this combinatorial Hodge theory and combinatorial Lefschetz theory. So you have a simplicial complex. And this is somehow, okay, so everyone knows what a simplicial complex is. I assume, right, you have some structure made out of simplices, and you embed it into a 2k dimensional space. All right, that's kind of the interesting. So a k-dimensional complex in a 2k dimensional space is kind of the interesting part. So you expect the intersections to be transversal if you just do it in general position. And then you ask how many k-dimensional simplicities can it have in terms of the number of k-1 dimensional faces. And this is a rather hard problem. So one reason is that you cannot, so in the plane, what we could do, we could add edges until every bounded, until every face, not bounded, every face was a triangle, right? Everything was a triangle, so it came from a triangulation of ambient space. And this is one of the things that you cannot do in higher dimensions. So a two-dimensional complex into R4, well, first of all, it's kind of, I mean, making it a triangulation, the three-dimensional face is missing, but you also cannot do it monotonically. So in fact, the embedding question is algorithmically very hard. So it's not, it's something that is impossible to do. So you cannot reduce it to something nice like a higher dimensional, somehow basically just Euler characteristic like we did in the basic case or in some other relations. So this is a really hard problem. So what can we do? Well, nevertheless, we can show now that we have the following bound. So the number of k faces is at most k plus 2 times the number of k minus 1 dimensional faces. Under a mild assumption. So we need that the embedding is PL. All right. And now what I want to do is I want to convince you that somehow for this, for these kind of things, algebraic theorems are important. And then I will basically give you methods to prove these algebraic theorems using combinatorics, because classical algebraic geometry just doesn't give us these theorems anymore. All right. Let me just note that somehow, I mean, the PL here is still necessary. We don't know how to get around that. All right. All right. So let's do a little algebraic geometry, and this is really just the basic kind. And we don't even, I mean, if you don't remember this construction, and I assume actually in this audience everyone will, but still, you can actually do this in a direct combinatorial way. So what we start with is a simplicial d-dimensional polytope, and associated to it, we can define a toric variety. Okay, so I mean, I need to assume that the coordinates are rational, but that's really not an issue. But even if you don't remember that toric variety, I mean, I'm interested in the cohomology ring only, and I can model it in two ways. So it's a ring of, I mean, one way to think about it, it's a cohomwise, so it is a ring of cohomwise polynomial functions, sorry. So this here should be polynomial. Cohomwise polynomial functions in the fan over the polytope. And then what I take out is basically everything that is boring in this ring, all right? So everything that does not see the combinatorial structure. So this is the idea generated by the global linear functions. That's it. And in a little more complicated or a little more abstract way to define it, but maybe somehow more informative, is this notion of the phase ring, or sometimes called Stanley-Wiesner ring. So what I take is, I take a polynomial ring. I could actually take any kind of field here. I don't really care, as long as the field is infinite or infinite, right? Finite and infinite. Right? So infinite, so that Noether normalization works. This doesn't matter. So I just take this polynomial ring. Each of the indeterminates I associate to one of the vertices of the simplicial complex, and then I take out two ideals. So the ideal I is somehow it's generated by the non-faces. So it's right. So this here is by the x to the alpha, such that the support of this multi-index alpha is not in my simplicial complex. It's not part of P. Then I have this additional ideal, which is kind of, this you should think of as the analog of the global linear functions. So this is kind of the boring functions. I mean, one way to think of this is that if I just take this quotient, then this is infinite dimensional as a vector space. So what I do is I want to take the Artinian reduction. I want to get an Artinian object. Then I take out a linear system of parameters. And this is somehow the length of this linear system of parameters. This is exactly the Kull dimension. So everything fits from the view of commutative algebra. All right, that's it. And now I have a ring. All right, so and this ring is nice and it satisfies all kinds of nice principles. So one that is in particular important, right? It behaves. I mean, so in this case, it actually is right. It is a cohomology ring of a rationally smooth variety. So really, I mean, that's now I'm really just making statements or retranslating really classical topology facts. So we have it's a cohomology ring. It's graded. So we have a fundamental class and we have a perfect pairing. This is just a Poincare pairing. That's it. All right. All right. So far so good. Then we have the following theorem. That is somehow the kind of one of the central theorems in the area. Is that, well, okay, so this is not only rationally smooth, but it's also scalar. Well, I mean, we have some mild singularities, but that's fine. And so what we have is the Hodge Lefschetz theorem of this variety, right? So what we have, okay, so we have an isomorphism, right? So we know that somehow the degree I part and the degree d minus I part, they are isomorphic as vector spaces, right? That's already nice. And here should be an L. But of course, that somehow you want to know this isomorphism more intimately, all right? And here's one way to give more meaning to this isomorphism, to give a stronger way to write this isomorphism between these opposite spaces. And this is that actually you can go from one to the other by multiplication within the ring, and specifically with the specific degree 1 function. So I have the class of a convex function on the fan of P, and I multiply from degree I to degree d minus I, so I have to take the d minus 2i power. All right, and here convex is again in this. All right, so you remember we had two models for this ring, and one of them was by the was looking at the Combinatorial polynomial functions. All right, and Combinatorial polynomial functions, in particular, this is a class. This is the degree 1 function, so it should be a Combinatorial linear function. And now I'm looking at exactly at the convex ones. Okay, so I'm taking the convex one on the fan and can multiply with that one. And that gives me somehow, okay, so this gives me the isomorphism, and this comes together. All right, so this is somehow the convexity. This is our notion of positivity. If you think about it, this is a scalar class. And what we have as well then with respect to that class is the Hodge Riemann relations. All right, so I can define this all-important quadratic form, and so once the index for some reason is up. I'm very bad at proofreading. So on the degree I part, and this quadratic form just takes, okay, so I want to take AI times some, right, an element in AI and another element in AI, but I want to get out the real number. So what I take is A times B times this power of the convex class, right? So power of the scalar class, and then I can evaluate it using the degree function. All right, so that's now a real number. Right, so the Hodge Lefschetz theorem just says that this form here is non-degenerate. But what the Hodge Riemann relations stronger say is that if I restrict to a subspace given by the kernel of this, well, not Lefschetz isomorphism, but Lefschetz isomorphism, but taken one further, then I'm actually definite of sign -1 to the I. All right, so on this subspace, I'm definite. Okay, so I mean, I assume that's the part you all know. So now we leave basically the realm of algebraic geometry. So from now on, right? So we have this theorem. It's good, but we want to go beyond that, and somehow we will now see several cases where we will need to go beyond this classical theorem, and I will basically explain first why and then how. All right, so here's the basic case where we can still define the ring, but we don't have the Hodge Lefschetz a priori. And this is, I can take a general, I mean, I can take any simplicial homology sphere. It doesn't actually matter, but I mean, for now I restrict to the reals. So let me say that there should be at least a rational, so characteristic zero homology sphere. I can still define this this ring A. All right, so I have the ring sigma. First I can define this non-phase ring just using the polynomial ring and the ideal generated by those monomials not supported in the simplicial complex, in the simplicial sphere. I get a ring. This is again infinite dimensional, but a finite full dimension. I take out some linear forms. I get this object. And this is again a Poincaré duality algebra. This was proven likely by Hochster, but Hochster did not write down everything he did. So it appears in later works by other authors who credit it to him. So I will do the same. And now I claim that the biggest problem is, okay, so we have the Poincaré duality algebra, but we don't have the Hodge Lefschetz theorem. Okay, and first of all, okay, you will see later why this is a big problem, why this is an important problem. But what is the issue here? Well, there are several issues in different situations, but one of the main issues here for this case is we no longer know what the Kähler class should be. There's no longer convexity, so we have no chance of talking about Kähler classes or positivity, nothing. All right, so that's good. If you want to make this precise, you can actually use some basic semi-algebraic results by Milner and Thom, that there is that for most spheres in a kind of enumerative way. So if you look at the random sphere on n vertices and randomly triangulated sphere on n vertices, then there's no chance of satisfying these Kähler relations or the Hodge Riemann relations. There's no Kähler class, so we have to do something about this. All right. So that's good. But okay, so let me just briefly motivate why this is important. So why is Hodge Lefschetz important in this context? And by the way, I mean, I realize this is not your area, so feel free to ask questions and stop me at any time, but also speed me up if I'm too boring. All right, so I want to just give this implication rather briefly. So I have my simplicial complex delta, right, and I wanted to embed it in a PL way into R2K. All right. Instead of doing that, I can of course embed it into a 2K sphere. All right, so I can embed it into a 2K sphere, and then I can actually, if it's a PL map, then I can actually do something rather basic. I can write this as a subcomplex in a simplicial sphere, so a triangulated sphere sigma. So this is sigma, a PL sphere that is it triangulates S to K. Okay, that's it. It's actually not important that it's a PL sphere, but I need to extend this to a triangulation. All right, and then in this situation, what I have is I can look at AK of sigma. And this is isomorphic to a k+1 of sigma. Why? Because of Poincaré duality. So it's a 2K sphere. So you remember the fundamental class lives in the dimension of the sphere plus 1, right? Because the dimension of the sphere is 1 less than the dimension of the polytope. So that's where the fundamental class lives. And now what I can do is I can look at the dimension. Okay, so I know that these are isomorphic. Let me look at the dimension of this space. So the dimension of, yeah, let me first look at AK of sigma. All right. So what's a nice way to bound the dimension from above? Well, I'm generated by the polynomials on the faces. So what I know is that this here is at most the number of faces in the number of k-1 faces in sigma. So that's good. And I can do this the same. I can do this also for the quotient corresponding to the subcomplex. So I can do the same for delta. I still have the same inequality. And what I can also do is I can look at the dimension of the space. Right, I bounded it from above now by basically giving you a generating system. The other way of bounding it would be I don't give you a generating system, I give you a generating system, and then I basically give a rough estimate for the number of relations. So this would be, okay, so I give you a generating system, so fk of delta. And then I have to, okay, so now I have to, okay, so now you have to think a little bit what it means to be rationally equivalent to 0. So yeah, what you come up with is that you get exactly k+1 relations for every k-1 phase, but they might be dependent if you look at them globally. All right. So that's the two inequalities that you have. And so this kind of basic inequality that I had at the start between the k phases and the k+1 phases, this now becomes this even more basic and nice inequality that ak of delta, sorry, dimension ak of delta, should be at least the dimension of ak+1 delta. All right. So, okay, how do I get that? Well, simple enough. What I do is, okay, so assume that I have this Lefschetz isomorphism, right? So I have then the map from AK to AK+1. Well, then I can draw a little commutative diagram that's really simple. So I have AK of delta to AK+1 of delta. And then I have the induced map here. But in this, the vertical maps are surjections. These are just the restriction maps to the subcomplex. And then, of course, if I have the Lefschetz map on top, right, this isomorphism on top, then I get this surjection at the bottom. And the surjection implies this inequality. So in particular, I get this, right, everything comes together. It's very nice, very simple. No, so nothing fancy. All right, so this tells you why Lefschetz is important. It's kind of, it's usually somehow these derivations of why Lefschetz is important are kind of clever, but I mean, there's nothing deep to them, right? There's okay, so that's it. It just seems to be a little game. But now we see that hard Lefschetz somehow we need hard Lefschetz, and I want to basically now go to prove hard Lefschetz or indicate how to prove hard Lefschetz be in these kind of cases, beyond algebraic geometry, and I will start with the case of matroids. Matroids is okay. So one way to think of it is you want to take an abstract way to formulate the concept of linear independence. So you have some vectors in some vector space, right? It's a collection of points in the vector space. And now you want to argue, okay, so what is an independent set? Well, okay, so in an independent set, is linearly independent set, it should satisfy certain. I mean, okay, so certainly a subset of an independent set is again independent. Then if you have two independent sets of equal size that are not the same, then you can shuffle an element from one to the other. So there's some kind of exchange. So there are some basic actions that somehow, some basic things, some basic theorems that independent sets satisfy. And you want to kind of form an abstract of that. So let me not go into the definition of a matroid, but that's kind of it. So it's an abstract structure that generalizes vector configurations in the same way that somehow a triangulation of the sphere would be a generalization of a polytope, right? And again, to matroids, you can associate a nice ring A. So first, again, as in the case of polytopes, in the case that it comes from a vector configuration, this actually is the cohomology ring, the drawing of a nice variety. So if you have some vectors in a complex vector space, what you can do is you can take the complement of the associated hyperplane arrangement, right? So you take not the vector, but you take the hyperplane orthogonal to it. This gives you a hyperplane arrangement. You can compactify the complement in a nice way, right? So that everything, so that the remainder kind of consists of normal crossing divisors. That's all good and nice. And then you have this nice smooth variety. Take its cohomology ring. That's my A. All right. And then, okay, so that's an old observation. And then, Feichtner and Jusinski, they observed that you can define this for general matroids. I will now give you the definition, although it's not the original definition really, but I mean, it's the one that I use with Johnny and Eric in our paper. So it's slightly different, but I mean, in the end, it's kind of isomorphic. So, all right. So what I take is, okay, so I start with the simplest of all matroids. That's the matroid of, right, so of general position vectors in a sufficiently large vector space. And somehow every subset is independent. Right. And now what I take is, again, the polynomial ring, where I take one variable for every independent set, actually, since everything is independent, I take one variable for every set. I take out, I take out the entire set for reasons. So I would just take proper subsets of the ground set, and I will not take the empty set. So these are the only two I exclude because they're boring. They're always there. And now what I do is I take a quotient of this object. I take this polynomial ring, and I quotient out two ideals. So the first ideal is essentially the analog of this non-phase ideal. All right. So what I want is to encode this matroid, the Boolean lattice. And so what should I take out? Well, what I don't want is things that don't come from the combinatorics of this lattice. So things that are not comparable, right? Because I want to have a poset structure. So I want to have that poset structure encoded. So everything that is not compatible with the poset structure, I take out. So this is the idea generated by this product phenomenon. All right. The second idea, this is essentially the analog. If I just took out the first, then I would have an infinite dimensional object again, right? So it would be the equivariant cohomology ring of a certain nice variety, the Promoter-Hero variety. So what I take out is essentially a very special linear system of parameters. So this, what I called theta before. And in this, to give it nice combinatorial meaning, basically what I do is I declare that you shouldn't be able to distinguish any two elements in this ring. So any two of the elements of the ground set you shouldn't be able to distinguish. So I basically say, okay, so I take all those variables containing a specific element and all those variables containing another element, and I take out the difference as a linear form. That's it. All right, and that's my ring. And now, okay, so this defines me this A of B. But now what I do is, okay, so every matroid here, every matroid I can see as a subset of the Boolean lattice. And now what I define is that A of M is naturally the quotient of A of B. All right, and how do I go to this quotient? Well, okay, so I kill all the right. I look at the lattice of flats of my matroid that I actually want to describe, and I basically just quotient out these elements. So this is defined to be AB modulo the ideal generated by the flats XS, not in M, not in the matroid. All right, so then I have it, now I have it for general matroids, this ring. It's nice and good. And here's the theorem that we get in this case. All right, so we have once again the Hodge Lefschetz and Hodge Riemann relations. And so first of all, okay, so to give you a Hodge Lefschetz and Hodge Riemann, I have to describe what it means to be Kähler. What's for this? Okay, so there is no geometric interpretation immediately. I could give you one, but it's, I mean, small. Then it's still an open variety, so it's small. So it's the incomplete fan, it's non-complete fan, but still. So let me just stay on an abstract level. So what I take is an element in the submodular cone. So what I mean is that, okay, so right, so any element L in this ring A of B in this bigger ring that is in degree 1, well, I can write it as a linear combination of the degree 1 elements. And now I can look at the coefficients, and these coefficients should form a submodular function. Okay. Now I take the interior there. Okay, a submodular cone, that's my Neff cone. Now I go to the interior of that cone, and that is my ample cone. And then I have this is my the function I picked. And now what I can do is I can again play the game of going to the Hodge Lefschetz. So I have, okay, so I have the Lefschetz isomorphism, and again it should be an I. There should be an I. So I have the Lefschetz isomorphism, and okay, so what is what else do I have? Well, I have once again the Hodge Riemann relations. Now this is very similar to the theorem that we had for polytopes, right? So this is very reminiscent of the convex polytopes theorem. The issue is that really this does not come in any nice way from the algebraic geometry picture. So we know that, for instance, you cannot really write down a smooth variety which encodes this ring in a nice way for general matroids. Basically, what we have is kind of a theorem that says, okay, if this cohomology ring comes in a nice way from a smooth variety, then the matroid itself must have been a configuration of vectors. Okay, so that's kind of disheartening, but somehow we prove it anyway by a combinatorial method. It's called a duck theorem because if it walks like a duck and it talks like a duck, then it is a duck. And if it walks like a toric variety and it talks like a toric variety, then it is a toric variety. And I should say that this is kind of not the first time that somehow a Lefschetz theorem was proven in this kind of artificial positivity, artificial scalar way. So for instance, there's the related work of Elias and Williamson in 2012. And all of them are based on, okay, there's also a work of Caru on the Hodge Lefschetz for intersection cohomology, or combinatorial intersection cohomology that I should mention. Well, all of these follow kind of the same idea, and this is due to McMullen. Let me actually see the time, because what time is it? Okay, so that's also good. All right, so the combinatorial motivation in this case is that from the Hodge Riemann relations in this case, so the Hodge Riemann, in this case, it's not Hodge Lefschetz that is important for us, but Hodge Riemann. And this implies the log concavity of the coefficients of a certain polynomial associated to the matroid. So you let me know if you want to hear more about this or want me to focus on this. I can also go back to it later. But essentially, this is a generalization of the chromatic polynomial. So if you have a graph, you can write down the number of colorings with n colors. And it turns out as a function of n, this is polynomial. But then you can look at the coefficients of this polynomial, and the coefficients of this polynomial form a log concave sequence. That's it. That's the motivation. All right. But I want to focus a little more on the proof idea, because that's kind of the interesting part. So usually it's about this. Okay, so this this Hodge Lefschetz and Hodge, the application of the Hodge Riemann is kind of it's some basic algebraic manipulation. It's not so interesting. So let me go to the idea for the proof. Okay, I already said that somehow the notion of submodular functions provides somehow the Nefco, right? And so now what we do is the following. There are two lemmas of McMullen that translate to the case of matroids. So the first one, the first lemma says that basically, if you have the Hodge Riemann relations in co-rank 1, then you get the Hodge Lefschetz in the dimension you are interested in. So for instance, you are interested in rank R matroids, but you have the Hodge Riemann relations in rank R minus 1. Then you automatically get the Hodge Lefschetz theorem in rank R. Right? So remember, the Hodge Lefschetz theorem said something weaker. It just said that this Hodge Riemann bilinear form is non-degenerate. In fact, it's weaker than the Hodge Riemann relations in the given dimension, but it's also really implied by the Hodge Riemann relations in co-rank 1. And now okay. So what do you do? So you have the Hodge Riemann. So now you basically do an induction. You have Hodge Riemann relations, and you have in rank R minus 1, you get it the Hodge Lefschetz in rank R. And now, of course, to complete this, you want to give the Hodge Lefschetz you want to get the Hodge Riemann relations in rank R, right? You only have Hodge Lefschetz. So now what you do? So you take one case, one specific matroid, essentially, where you know the Hodge Riemann relations. There's always one very simple matroid like that. It's essentially, there's a matroid that basically is projective space. Okay, so there's the Turing is just projective space. So in particular, you know that somehow on this matroid you have the Hodge Riemann relations, because, well, yeah, it's projective space. What you want to do. So you have Hodge Riemann relations there, and now there is an operation to go between any two matroids from one to the other in a kind of continuous way along something that is the analog of birational transformations or flips. And now, okay, what do I know? So I go from matroid A that I know to matroid B that I don't know, right? I deform this continuously. What do I know? I have the Hodge Lefschetz along the way because I have the Hodge Lefschetz from codimension 1. All right, so from matroid A that I know, I go to matroid B. I know that the matroid A satisfies Hodge Riemann relations, and I have Hodge Lefschetz along the way. But what does Hodge Lefschetz along the way say? Well, it says that, in particular, it says that the bilinear form never degenerates. All right, so I cannot just flip sign, right? Because if I flip sign, then I must degenerate at some intermediate point, right? That's just intermediate value theorem. So I cannot change sign. So in particular, I must have the Hodge Riemann relations also for matroid B. I mean, there's something more to be said because these flips, they change the cohomology in a slightly subtle way at some points, or at some singular points. But then at these points, you can basically split off. You can split off a factor that you understand, and so it doesn't really affect you. So that's it. So this is essentially the whole program, and it's really small. Actually, this goes back to a rather classical work. It's somehow this idea was repeated again and again, but that's it. All right, so classical idea. It's just that somehow the main thing was to define these birational transformations, and that's to come up with this continuous deformation. But otherwise, it's a kind of classical argument. All right. Now that's the Hodge Riemann relations in this case of matroids. And now I want to basically go back to the Hodge Lefschetz theorem in the case of spheres, because I want to highlight one more case where we have the Hodge Lefschetz theorem, but we don't have it explained from algebraic geometry, from an algebraic geometry standpoint. And now it gets a little more complicated. So now I go to spheres. So here I was able to find a notion of what it means to be Neff, what it means to be ample. All right, so matroids are actually, well, they're not so bad. Right, so there's a notion of ample. That's something good for us. But for spheres, we don't have that. What we have instead is, okay, something that comes from its basic idea comes from work of Kazhdan and Ziegler, and this is a notion of general position algebraic geometry. So what I will talk about. Okay, so I actually restricted to PL spheres here because I wanted to explain part of the somehow proof in detail for PL spheres, but I think I won't get to it. So the general theorem that we have is actually without PL spheres, and because I don't get to the proof of this theorem anyway, it's not necessary to restrict to PL here. So the explanation in the paper is more general, and since I won't get to the explanation for the special case anyway, forget that I restricted. All right, so I have any simplicial homology sphere. All right, and now what I take is, all right, so you remember that, so how was this A of sigma defined? So I had A of sigma. This was defined as this polynomial ring R of sigma, R of x, sorry, modulo this non-phase ideal. And then what I took out is an additional ideal theta. All right. And of course, here, okay, so here I don't have a choice really. There's no, this just combinatorially determined from the sphere. But this here, right, this here is this linear system at theta. I have a lot of choice, right? I could do whatever. All right. And so I have a whole moduli space of possible choices theta that I can choose from. And now let me take a generic one of those. Right, I have an open-end set somewhere that I won't describe further, but now I pick a generic one. Right, I mean I could, for instance, take a transcendental element, and then what I do is I pick that element and I pick a generic, then I go again, now I don't have convexity, so I again look at the generic degree 1 element. Then we have the Hodge Lefschetz theorem. All right, so we have an isomorphism between degree I and degree d minus I. That's the analog of the Hodge Lefschetz theorem. And we have something that replaces basically the Hodge Riemann relation. So we have again the same quadratic form. All right, so we have the same quadratic form here. So it's the Q, that's just the same thing. It's just again A times B times L to the G minus 2I. But I can no longer say anything about any property of the sign of the signature. Instead, what I say is at many subspaces, this is actually non-degenerate. So if I restrict this Hodge Riemann bilinear form to, in particular, the subspaces generated by square free monomial ideals, then I'm actually the Poincaré pairing on the more generally this Hodge Riemann pairing do not degenerate. That's a kind of strange property, right? Somehow it's a it seems kind of without precedent at first sight. It's somehow it's very strange. It's now we found it by accident, or I originally found it by accident, and this led to the 2018 proof. And then two Greek mathematicians, they found the same property again in a different context. So actually, they with Papadakis and Petrotou, we extended this to general characteristics. So there's no this here you can define. I should say you can define over any field. So this can be k of x modulo I sigma plus theta. So, and then I should also write k. So any field is fine, and any characteristic is fine. And so they discovered this again over characteristic 2 as a nice property, and then it's proved the Hodge Lefschetz theorem once again in characteristic 2 at first, and then we kind of extended their partial proof to general characteristic again. So this seems to be the right property for Hodge Lefschetz beyond positivity. So let me try to explain a little what is going on here. So where does this come from, and where does this how do you prove that then? Before I do that, okay, so I can so what is this useful for? Well, I already said, okay, this in particular implies this Grünbaum-Carlyle-Saccaria conjecture. It implies statements about phase vectors, so the possible phase numbers of simplicial homology spheres. It implies results about, well, the size of a triangulation of manifolds. So how many vertices do you need to triangulate this given manifold? So that's the thing, the type of thing it's useful for. While this is all good and nice, I should say that these Hall-Laman relations, they are kind of transversal to somehow. You should not think of them as somehow as in any way reducing to the classical Hodge Riemann relations in the smooth case. Let me see whether I have a free slide here. Oh yeah, I have a free slide. Okay. And this is somehow, I can give you a nice variety, a super nice variety that somehow everyone knows, where the whole Laman relations are not satisfied, even though the variety is smooth. So generic is really somehow a critical point here. And this small variety that I will talk about is really just P1 cross P1. So the fan that I have is really just this one, right? It's just this fan in R2 or Z2. And now, right, so you can think of it as a fan over the two-dimensional cross polytope. All right, so this is my sigma. And now, what is it? What does it mean to be a square-free monomial ideal? Well, you can look at the square-free monomial ideal would be an ideal generated by any choice of these rays. And what could I do is I could, for instance, take the ideal generated by this ray. All right, so by the Cartier divisor here. So what would happen if so I have this ideal generated by a single degree 1 element, right? And the whole Laman relation. So this is a variety in dimension 2. So I have a fundamental class in degree 2. So the whole Laman relations will tell me that if I multiply that element here with itself, all right, so this small, let me call this element just x, that the whole Laman relations say that x squared should be non-zero. All right, so x squared should be non-zero, right? Because I shouldn't degenerate on this element. But in this case, you will see that it clearly does. All right, somehow you can, if you compute it, x squared is equal to 0, so you're in trouble. However, so what's the point of the theorem? So the point is what I can do is that I can find a fan with the same equivariant cohomology on which the whole Laman relations is true. So if I just take this fan generically, let me actually do this a little more generically. All right, so this is the same combinatorics. All right, so the fan is now this one here. And it turns out that if I compute the square of an element now, then it will be non-zero. And in fact, this you can show. This has the same equivariant cohomology. The theta was chosen differently, so the cohomology ring is really different now. And now I satisfy these whole Laman relations. So you can compute somehow the analog of this element squared, and it will be non-zero. The trick for the drawing is here that no two of these divisors here lie on a line. So that's a criterion. So no two of these here they form a line. Here, these two do not form a line. So that's the whole issue that happens to appear. Okay, so the whole Laman relations are not nicely reducing to the Hodge Riemann relations in the smooth case, so they're really different. But now, okay, so how do I prove that? So how do I prove the Hodge Lefschetz and whole Laman relations, and how are they connected? All right, so I explained that somehow in this classical McMullen proof, Hodge Lefschetz and Hodge Riemann, they're intimately connected. You prove them kind of together. And here the same thing happens. The basic result that we need is a lemma due to Kronecker. Let me actually not spoiler for a second. How is this done? So, all right, this basic representation theory of the Kronecker quiver, but let me just explain it over in very small, just linear algebra terms. So I have two maps between vector spaces X and Y. All right, so you think of these as, these are the two opposing degrees of your, these are the two opposing degrees of your vector space. Sorry, of your Chow ring. So this is degree I and degree d minus I, and I have two linear maps between them. All right, so think of A as kind of your candidate for the Lefschetz map that you already constructed, and B is a way small. It's not quite an isomorphism yet. So in particular, it's not quite injective yet, but you want to make it better. You want to make it a better Lefschetz map. So what you want to say is, okay, so if you have two linear maps, all right, so how small can the kernel of their linear combination be? Well, the kernel could at best be the intersection of the kernels of the individuals, right? So that's the best that you can hope for, all right? So you want to improve your map, make the kernel smaller. That's the best that you can reach. And here's a criterion under which this is satisfied. So if I take the generic linear combination of these two maps, the kernel will satisfy this, provided that if I map the kernel of A under B and intersect it with the image of A, that is, the intersection is just 0, right? This trivial intersection. Provided I have that, I get this somehow. I really make the kernel smaller. So what you have a candidate for a Lefschetz map, and then you have some hint, some idea on how to improve this. Some map B that you think, okay, could make this kernel smaller. In particular, well, why I will explain in a second why you can always find this, but that's what you want to do. Okay, make the kernel smaller. The idea then is to do this iteratively, right? Okay, so you multiply, you start by a map that you know, right? So a map that you know well is just multiplication with one of the torus invariant divisors, so one of the indeterminates. Those kernels you understand, and now once you have, right, so you multiply just with the one of the variables, and now you multiply with another variable, all right? You want to take the generic linear combination of those, and then say that the kernel of the generic linear combination is exactly the intersection of the kernels. Poincaré duality tells you that if you have this property, right? If you did this for iteratively for all the vertices together, then and you have this property that the kernel of this generic linear combination is the intersection of the kernels, then you're done, because this here, right, for this here is equal to 0 if W is the vertex set of sigma. Why is that? Because of Poincaré duality, right? Poincaré duality tells you that every element you must be able to multiply non-trivially with some other element, in particular with some degree 1 element. So the kernel cannot be the kernel of the multiplication with all of them cannot be 0. So, or in other words, the SOCL does not. The SOCL is just concentrated in the top degree. So in particular, this would be, then you would be done. So this is okay. So proving this. Okay, so now you want to prove this iteratively. But okay, so I didn't tell you. Okay, so why is this? Why on earth is this in any way connected to why is it in any way connected to the to this Hall-Lamarr relations? Well, okay, so let's look at this. Let's look at this condition here. Right. So I have this image of A. Right. Image of A. I should think of this. A is the old map, and B is somehow B. Now I should say that B is now a new vertex that I want to add. So B is somehow the new variable. So let's look at this now from the perspective of the spaces that we're really in. If I look at the kernel of A and the image of A in this point in my intersection ring, then they are really orthogonal complements. All right. Right. So they are exactly they are under the Poincare pairing, they're exactly orthogonal on each other. Now, if so now I pull back along XV. So this is just a pullback to some prime divisor. All right, so that's okay. So this will not affect the fact that they are orthogonal complements. Now they are just orthogonal complements in the pullback. And now what I'm saying is, okay, so I'm looking at orthogonal complements in a Poincare duality algebra, and I want to say that the intersection is trivial. Right, but that's okay. So orthogonal complements intersect trivially if and only if the pairing does not degenerate, and I restrict it to any of the two spaces, right? I mean, just basic linear algebra. There's nothing fancy here. All right, so here you have the criterion. So the pairing, somehow not degenerating, gives you exactly this way of extending of improving your Lefschetz map until it is indeed in the Lefschetz isomorphism. Right, so that's it. So the pairing, if you think about it, though, it's a pairing in co-rank 1 because it's a pairing in the pullback to this prime divisor XV. So it's again, there's an induction going on. So this pairing property in co-rank 1 really implies a Lefschetz in your given rank. That's it. All right. Now, I mean, okay, so I wanted to say something on why it's called Hol-Laman. Let me actually, that's not good. Okay, so yeah, let me not say anything about that. And okay, let me skip. And if you want to hear the long version, like 12 hours of the explanation, then you can watch the Hadamard lectures on YouTube. That's the detailed explanation of the proof. But thank you.
Thank you also. Are there questions? Also online, feel free to ask.
I guess the Americans are not awake yet. Yeah, otherwise overcooked.
Okay, so it doesn't seem to be the case. So thanks again for your talk and